Today we're going to start looking at unsupervised learning. We'll still see some things related to supervised learning, mostly here in feature selection, but we're going to start to go outside that framework of trying to train a model to get some hypothesis that is being fitted in order to predict some value that we have in our data. And we're going to start looking at other applications of machine learning where there may not be a goal to actually predict something that is in the data, but rather we want to understand the data. And this is a basic idea of unsupervised learning, which is basically a broad range of applications that falls outside that supervised scheme that we saw previously, and we're going to start looking at problems of data visualization and feature selection in this first lecture. So the idea of unsupervised learning is different from what we've been seeing so far, in that we are not considering labels or target values in the training set to which we want to make some prediction or which we want to approximate. So we are not using some error measure to optimize the parameters of our model or try to find the best hypothesis. The goal here is to find structure in data. So basically, you can imagine that what we do with unsupervised learning is a transformation of whatever features we have initially in our original data, and after it goes through the learner, we obtain new feature values. We don't obtain a prediction or something like that. We are not trying to approximate some target values, but we are trying to find different representations of the data or new features that help us understand something about the data. So the idea of learning without using labels does not mean that data cannot be labeled. You can take labeled data and still do unsupervised learning, like grouping similar elements together, visualizing, transforming the features, and so on. But since we are training without having to adjust our predictions to known values, so that scheme that we follow in supervised learning, since we are not doing that, we can use unsupervised learning either with labeled data or unlabeled data. It's possible to use unsupervised learning as a prior step to supervised learning. So suppose you have a classification problem, but you can benefit from doing something to the features, transforming the feature space in some way that has nothing to do with the actual labels, and then train your classifiers in that new data. So data visualization, understanding data, estimating distributions, selecting features, extracting features, clustering these may all benefit from these approaches and supervised learning. And we are going to focus a lot on clustering in future lectures. Also, dimensionality reduction, feature extraction, we are going to mention a bit of those things here. In this lecture, I'm going to talk about visualizing data and selecting features, which can be done both with labeled data and unlabeled data. So we are still bridging a bit the two subjects, supervised and unsupervised learning, but this is a more generic approach that you can also use with unlabeled data. Okay, so let's start with a brief introduction to the problem of visualizing data. So far, I've been showing you diagrams and plots in classification, regression, and those examples always in 2 dimensions. And the reason for this is that visualizing 2-dimensional data is very easy. We have a 2-dimensional surface in the computer screen, so we just plot the data and we can see everything. Of course, more realistic data sets have a lot more features than just 2. And so when you start working with things over 3 dimensions, then you have a problem trying to visualize them. To use just a very simple example, we'll go back to this iris data set. So if you recall, we have these 3 species of flowers, and we have these 4 attributes. So the length and width of the sepals and the length and width of the petals. This means that our data is in 4 dimensions. Then we have the class labels, but the features are in 4 dimensions. So we cannot just plot our data simply in these 4 dimensions, and we need to resort to some visualization techniques to help us understand what the data is like. We are not going to focus too much in detail on visualization. This is just one part of this lecture because it's an important part of data understanding and data analysis that usually accompanies machine learning. So it's risky if you try to do machine learning without understanding your data first. And visualization is an important tool for understanding data. So these are just a few examples of things that you can do when you need to visualize data that has too many dimensions for us to even imagine the data itself. So I'm going to use Pandas. This is Python data analysis library. This is not required. You don't need to learn Pandas for this course, but it's useful because it gives you wrappers to lots of more fancy plotting options. It has objects to handle data tables and to do statistics and things like that. So if you're doing data analysis, it's very useful to learn Pandas. Here we mostly focus on scikit-learn, but for this lecture I'm going to take advantage of the convenient plotting methods that Pandas provides. So one thing that we can do is to examine the distributions of individual features. And this we can do, for example, with histograms. All these examples you could theoretically do just with pyplot, but Pandas makes it a lot easier to do with little code because it provides these wrapper methods for the plotting. So this is our data file. This is a CSV file. We have the first row with the column headers. These are the 4 features, the sepal and petal dimensions, and the last column is the label with the name of the flower. We have these 3 flower species. We can easily load this if we use read CSV from Pandas. This method allows us to read a CSV file and provides a data frame. A data frame is an object in Pandas that makes it very easy to deal with tabular data. So if you have a table, you have the columns indexed by the names. You can it automatically identifies the type of values that you have in the file, so strings and floating point numbers and so on. And also this object, the data frame that you get when you read the file, has its own plotting method. So in this case, I want to plot a histogram. I specify here in the kind argument that it's a histogram, the number of beans, and transparency, so that when I see them overlapping, Pandas will automatically draw one distribution for each of the numerical features, and it identifies the string feature, the text feature, to be classes. So it's going to use that one to separate the different plots. We can control a bit more this behavior if we don't want to use all the columns or things like that. It's easy to do those kinds of manipulation in Pandas, but for this purpose we are just going to go on automatic, not worried much about the codes, and just look at the results. So the idea here is that we have in the same plot the histograms of the different features. So we can see that some features, for example, sepal width is very concentrated here, petal length is more distributed over here, and so on. So they are at slightly different regions in this plot because the dimensions are different, and we have an idea of the different distributions. If you want, you can also do this without overlaying the different distributions. So if you use the histogram method on your data frame, you can plot a matrix of plots with the histograms of all of them. So these are for the width of the petal, the width of the sepal, and the length here. So this allows us to take a look at the data, each individual feature separated from the rest, and we are looking at the distributions of the features with a histogram. Another way of looking at the distributions of individual features is a box plot. The box plot looks like this, and it has these lines representing the median. So this is where we split 50% on either side of our distribution. Then we have these boxes that represent these two middle quantiles. So from 25% of the points to 75% of the points are here. So 50% of the data of the length of the petals is inside this box, and the rest is outside here. Then there are these whiskers, these lines here, that are placed in the extremes of our data that do not go outside this range. So taking the interquantile distance, this distance between 75% and 25% of the data, and multiplying by a constant. So usually this is 1.5. So you imagine that you have this distance here, and you multiply it by 1.5 and go up, and 1.5 and go down. So whatever is inside this region, that is 1.5 times the interquantile distance, is considered to be inside the normal distribution, and the whiskers are placed at the smallest point that is above this value here. Here, and the largest one here, so that we have an idea of how the majority of the points and the normally distributed points here are in this range. So for example, here we can see that we have a greater spread to higher values than to lower values. Here too, here is a bit more symmetrical. But then there may be some points that fall outside this box. So in this case, this counting 1.5 times this range up and down is enough to span all the data, so we don't have outliers. In this case, we have some outliers, because if we count 1.5 times this range up, we still have some points that are even higher than that value. So outliers are shown individually with these circles. So looking at this at the box plot, it's easy to have an idea of how asymmetric the distribution is, if there are outliers far away from the normal range of points, how the distributions range, and so on. And it's easy to compare different distributions. So if you have lots of features and you want to compare them, the box plot is much clearer than, for example, looking at histograms or overlapping all the histograms, because if you have lots of features, this can become confusing. So both the histograms and the box plot only allows us to look at individual features. We are not seeing how the features relate to each other. So one way of looking at how pairs of features relate to each other is this scatter matrix plot. You have a function for computing the scatter matrix in the plotting module in Pandas, and you just call the function with your data, and you have options like the size of the figure, the transparency, and so on. So you can create this sort of plots where the scatter matrix function will use the numerical columns in your data and will plot them in pairs. So here you have the four features, the sepal and petal length and width. Here the same four features, and here you have the combinations. So we have here sepal length and petal width, and this is how they are plotted one against the other. If you have something like this, for example, you can see that there is a strong correlation. So petal width and petal length are strongly correlated, because you can see these fall very much on a diagonal. If you have something, a spread like this, a cloud like this, then you see that these are not strongly correlated. They seem not to be too much informative one about the other. In the diagonal, you would have the features plotted against the same feature. So this would not be informative, because it would always be a straight line. If you plot the same coordinates on the x and y axis, you just get a diagonal. So in the diagonal of this matrix of scatter plots, we have the distribution of each feature. If you plot this with this option of kernel density estimation in the diagonal, you get this plot. If you use the histogram option, you get a histogram on the diagonal. But the scatter matrix allows us to, at a glance, check for correlations between features that are not that much correlated, and to look at all the combinations of pairs of features and visualize these correlations. Of course, pairs of features is about the limit that we can do with this sort of plots, because if you now go for 3 features at a time, you need 3-dimensional plots, and it will be a huge matrix, very confusing, and more than that we cannot even imagine. So there is a limitation to how much correlations between features you can understand, and if you have many features, this can become confusing. Another way of looking at data in higher dimensions is to use this parallel coordinates plot. So in this representation, each data point is represented as a line, and we use a parallel coordinate axis here in the vertical for the different features. So one line here goes from the sepal length to the sepal width to the petal length and then the petal width of the same flower, of the same example. So one line here is one flower, and it spans the different values that flower has in the different features. And so we do this for all the flowers. Each one contributes a line, and you can easily do this with the parallel coordinates function in the plotting functions in Pandas. And so you provide your data frame and the name of the column that has the different categories. So this is meant usually for data that has some kind of label for categories. So the parallel coordinates plot will automatically change the colors and show you the representation for the different species. So what we can see in this kind of plot is how the different features relate in each example. And also we can see that, for example, here this Setosa species seems to have a lower values for petal length and width than the other two, and Virginica seems to have the highest values here. So we can see that they are plotted in different regions of these axes, whereas, for example, for sepal width, there doesn't seem to be a strong correlation with the species, and here also they seem to be a lot mixed together. So you can get an idea of how the data is distributed in more than 2 or 3 dimensions by looking at the shape of these lines. There are also other interesting properties of parallel coordinates plots when you have high correlation between features, negative correlation, positive correlation, and so on. And you can see that easily on the parallel coordinates plot. We are not going to go into much detail there, but this is one way of representing data in more than 2 dimensions that makes it simpler to grasp some features about the data, some relations between the different features. This parallel coordinates function is meant for this kind of views when you have some column that has categorical values and to distinguish between the different series. But it's easy to, if you want to just show everything with the same color, or if you don't have those kinds of labels, it's easy to just create a new column with the same label for everything. So imagine that we had in our data only those numerical values and not the labels. This we can do if we go to the original data frame and ask only for this set of columns. So we are not getting the name column, we are getting only the feature values. And now to this new data frame that has only the features, we add a name column, that is equal for all the examples. So this pandas does broadcasting like NumPy. So this is a column in our table, and we are setting all the rows to this value all. So everything is the same, and now we can plot the parallel coordinates, and we get everything with the same color. So this is one way you can use this function to show these images all in one color, or to use this function if you don't have in your data some labels. So if you are dealing with unlabeled data, you can still take a look at the distribution of these lines and see that there are some points that are clearly different from the rest here. Another way of looking at multidimensional data using lines is these Andrews curves. So we have each data point as a set of features in many dimensions. So x1, x2, x3, and so on. We create a curved line by adding sine and cosine components at different frequencies for all the features. So the first feature is just a constant here, telling us how high and low the curve will be. The second feature will multiply a sine wave with a period of t. The third feature is a cosine wave with the same period. And then the fourth feature, a sine wave with twice the frequency or half the period, and so on. So we can add higher frequency waves the more features we have. This is easy to do also in pandas by using the Andrews curves, and this is the effect that we get. So we are adding higher frequencies multiplied by the different feature values, and we can see that this pattern here, for example, for setosa, is different from the one in versicolor here in green, and we can see some difference between virginic and versicolor also. So it's easy to see these different curves representing the different points in our data. One disadvantage with Andrews curves is that it's a lot less intuitive to figure out what is happening here, because we are adding the amplitudes at different frequencies, whereas with the parallel coordinates plots we have each feature on an axis. Of course, all of these have one drawback in that they are dependent on the order of the features, on the order that you use the features in. So these lines will change if you change the order of the features, and if you have many features, this may be a problem and may make it hard to understand data. But in general, if you have data with many features, then you have to face the fact that it will be hard to understand. In some future lectures, we're going to talk a bit about that dimensionality reduction. Also, we're going to see here one way of doing that with principal component analysis, but that is also a big problem in general when you're dealing with high dimensional data. Another way of visualizing the contributions of different features is this radial visualization, or RADVIS, which creates a plot where you have the different features in a circle, and depending on the proportion of the magnitude for each feature in each point, it will be pulled more towards one side or the other. So if there is a balance in the magnitude of the features, the points tend to fall more to the center. If one feature dominates, the points are pulled in that direction. If two features dominate, then they will be pulled somewhere in between the two, and so on. So this spreads out our data. It represents each data point as a point, but it spreads the points outwards in this circle by pulling them towards the features that have largest values. Okay, so in general, there are other plots that you can see. You can see the tutorials on pandas for visualization. There are lots of different options, but this is not so much part of this course to detail this visualization. The idea is that the important thing is this idea that visualizing data in more than 2 dimensions tends to be hard and usually is a problem. So that's why in most examples I give you, I use synthetic data in 2 dimensions. Otherwise, it would be difficult to follow what's happening. But it's important to understand the data, and we generally need some way to try to see as best we can what are the distributions, what are the relations of the data, and so forth. So you can use histograms, kernel density estimation, box plots, that kind of tools to look at the distributions of individual features. You can also use kernel density estimation to look at distributions of pairs of features, but then if you try to put more features together at the same time, you need more dimensions, and again, the same problem. There are some ways of representing relations, like pairwise scatter plots. These allow us to easily find pairs of features that are correlated or uncorrelated. But if we want to go beyond looking at pairs of features, then we need things like parallel coordinates, the Andrews curves, RAD-Vs, and things like that, that try to represent how the different features interplay with one another. But one thing to remember is that every time we do this, we are actually losing a lot of information about the actual cloud of points that we have. But this is because of our limitation. We cannot imagine things in more than 3 dimensions, and even visualizing things in 3 dimensions using the computer requires some additional techniques like rotating things and techniques like that. Okay, so another problem that we're going to address today is the one of selecting features. This is often used in the context of supervised learning, but can also be applied to unsupervised learning. So the idea here is that not all features may be equally useful. There may be too many features, and then our models start to overfit, for example. So if we use all the features, we may have actually less performance than if we use fewer features. We may have features that are too noisy, or we may have features that are expensive. So suppose that you are doing trying to make predictions with medical diagnosis and things like that. So measuring the temperature of the patient is very cheap and easy. Doing magnetic resonance or things like that takes very expensive equipment. So you may need to decide if your model really needs that feature to make good predictions. So basically, the reasons for selecting features may be varied, and some include details about the actual process of measuring the data. Some, if you are using, for example, supervised learning, may be related to reducing overfitting and so on, but they may be related also to simply trying to simplify your data set to understand it better, and such. So there are many different situations where it may be beneficial to discard some features and select others. But yeah, the question now is how are we going to do this? One approach is to look at each feature individually, and if we are trying to predict something, if we have some labels in our data, then we can try to check if the features are correlated to the label. So if each individual feature is correlated to the label. One possible test for that is the statistical chi-square test, which this distribution occurs if we have independent random variables here. So we have random variables that can be 0 or 1, for example, our class labels. And if the prediction given some feature, or where the feature is correlated, or if you are just measuring the percentage of elements in one class in one feature, for example. So this can be used whether inside looking at the results of some model that is doing the prediction with a single feature, or you can just take the feature and measure, for example, the fraction of examples in one class that have this particular feature, for example, for a categorical feature. But the idea here is that if what you expect by looking at that feature and what you observe in your class labels is independent, then the chi-square test, this value will follow the chi-square distribution. And so basically, when you do this test, you'll get a high probability of this happening by chance. If you get a very low probability, then this means that there is a correlation between the feature and your labels. A more used test that you probably know from statistics is the analysis of variance test, where you can measure variance between different groups, for example, between classes when you have a classification problem, and the variance within the classes. So this fraction, this proportion here, will be distributed with this F distribution. And so you can test what is the probability of obtaining some relation between the variances between classes and the variance within classes if there is no correlation between the two. So between the features we are measuring and the classes that we have. If the probability is very low, then the feature is likely to be correlated with the class. And the lower the probability that we get, the higher this correlation will be. So this is actually something we have in scikit-learn to help with feature selection, which is this F-test for classification that you can use with your data, so the features here, and the target values. In this case, the features are the sepal and petal dimensions, and the target are the three different species. You can actually load this data set in the from scikit-learn, because this is such a widely used data set for examples that you have the data set there. And the result will be something like this. You have actually two vectors with the F score and the probability. So the higher the F score you get, the lower the probability of getting that value or above. And you can see that features 3 and 4 are those that are more correlated with the classes. So we see that we have a very high F score and also a very low probability of this happening by chance. So 10 raised to minus 91 or minus 85 would be the probability of finding this correlation simply by chance if there was no relation between these features and the class. So now one thing we can do if you want to turn this from 4 dimensions to 2 is to just use these last two features, and we can plot them, and this is the result. So you see they seem to be quite correlated with the class, and we can see a good separation between the three species just by using these two features. So you can use, this is actually encapsulated in this select k-best univariate filter in scikit-learn, where you specify what is the function that gives you the score. For example, we can use the F-test. We specify how many features we want to retain, and now we select the best k features. We can just do fit transform. So this is a method that you'll often find in scikit-learn that first does the fit with the data and then transforms the input data and gives you the result. So in this case, the transformation consists in selecting only the features that have the largest score and outputting those in this matrix. So you input the matrix with the 4 features, you get the 2 best features by using this select k-best with k equals 2. Okay, so this allows us to compare each attribute, each feature to some variable, but it requires us to have those target values. We can then use the result for supervised or unsupervised learning. We can use both, but we need to have these target values to compute our correlations with. There are several measures of correlation that we can use, Pearson correlation, mutual information, and so on. But the idea is that we are trying to select the best feature to uh, according to this criteria of correlation with some label that we have in our data. We can also do feature selection with a univariate filter that is based on a model. So you can imagine training a very simple model with each of your features and pick the ones that give the highest performance in your model. So these are basically wrapper methods. We are going to look a bit more on this in a few slides. But this looks at each feature individually. And you can see a problem with that here is that even though this feature here is quite correlated with the species, we have one species in this range, another in this range, and another over here, and this one is also correlated with the species, the two features are very correlated with one another. So the problem we have here is that even though each one of them individually is pretty good, together they don't give us much information over what one of them would give. They are basically telling us the same thing. So we can see that there are two important aspects here to selecting combinations of features. Not only what each feature individually is telling us about what we want to know, but how the features combine with one another to complement each other. So this brings us to another type of filtering, which is multivariate filter. We basically want our features to correlate with whatever we want to predict, say the class or something like that, but we don't want them to correlate with each other. And these are the two fundamental concepts here. A feature is relevant if it correlates with the class. This you can do in the context of, at least if you have data that would allow supervised learning, so you have these target values. But a feature can be redundant if it correlates with another feature. So if you have features that are telling you the same thing, they are too much correlated, you don't need to have them both. You can discard one and keep the other. And this can be done with unsupervised learning because it doesn't require any labels. So we can use wrapper methods to try to figure out the best combinations of filters, and this is the way we do this is we use some score to perform to measure how well the features perform with some model. This can be, for example, a classification model, and we can use the accuracy or the error measures. But we can also be doing, for example, clustering with unsupervised learning, and we could try to measure the quality of the clusterings. But what we need is to have some way of measuring the performance we get when we train our model with a particular set of features. And now we need a search algorithm that will try different combinations of features to find out which combination gives us the best performance in our model. So in general, when we use a wrapper method, we are using the same model, the same machine learning algorithm that we want to use in the end with the ideal set of features. Sometimes it may not be the case if there are problems with performance, with the speed with which we can train our models, but usually with wrapper methods we are using the same models for selecting features as the ones that we are going to use in the end. There are basically two ways of doing this, of exploring these combinations. We can do it deterministically, either going forward, adding one feature at a time. So for example, imagine that we test our model with only one feature and we check each individual feature. We pick the best one. And now we add to that feature each of the other ones individually, and we pick the best combination of these two features. Then we do that with the third, the fourth, and so forth, until we either reach the desired number of features because we have some limit, or we stop improving and we retain that number of features. We can do it backwards. We can start with all the features and see which one we can eliminate that results either in the lowest degradation of performance or the most improvement in our performance, and we keep doing that, eliminating one at a time until we reach the desired number. If you have a small number of features, this can work fairly well. You just try these combinations, but you are missing too many combinations here because you're going greedily one feature at a time. So sometimes if you have a lot of features, or if there are many different combinations that can be useful, then using a non-deterministic wrapper may be best. You are trying random combinations of features, and by using some search heuristic like simulated annealing, genetic algorithms, things like that. But the idea is to check how well your model performs with combination of features so that you find the best combination for the task that you want to achieve. There are also embedded feature selection methods in which feature selection is already part of the learning algorithm. For example, with decision trees, you get the more relevant features higher up in the tree, and eventually features that are not even relevant may not be used at all in the decision tree. So a decision tree is actually selecting the best features. You have things like feature-weighted naive Bayes and things like that that can use different weights on different features according to how useful they are. And also you can use regularization to do feature selection. For example, N1 regularization, where we are penalizing the sum of the absolute values of the parameters, will tend to force some of the parameters to zero. So if you have a linear classifier with L1 regularization, those parameters that go to zero and the features corresponding to those multipliers will be features that will be discarded by regularization. So in scikit-learn you can do this with logistic regression, for example, with L1 regularization, and all those multipliers that go to zero tell you which features were discarded during training because they don't appear to be useful. So basically we have this approach. We can apply first a filter independent of the learning algorithm, doing some statistical tests on our features. We can use the machine learning algorithm to search for combinations of features by evaluating the result we get when we train with different combinations of filters, or we can use machine learning algorithms that can select the best features, for example, depending on the regularization or the algorithm itself. Okay, so to sum up this part, we took a brief look at the problem of visualizing data and also feature selection. So this problem that we don't want to use all the features, we just want to select the best ones. In unsupervised learning, we are looking at this sort of problems in a sense of basically trying to understand the data, finding structure in the data. Although feature selection is generally more used in supervised learning than unsupervised learning, you can use both, and you can use wrapper methods in unsupervised learning for feature selection, for example, by looking at the quality of clusters, etc. If you want to see more about this, this distinction between different types of feature selection methods, I based myself on this paper on feature selection techniques. You have tutorials on feature selection in scikit-learn, so you can see examples of how to use those objects, those classes for feature selection. If you want to learn more about visualization, it's easy. You can search for Pandas, the tutorial on visualization. It has lots of examples. So that one is just about looking at the recipes and different visualization methods. Okay, let's take a short break, and we continue in 10 minutes. So 5 minutes before 5 o'clock, I'll start the second part.